turn them on?
Yeah, the button. So this is soft. This is soft. Yeah. On. On. So we will be talking into this one. Okay. So and we keep it there when we do the presentations, and then when we have questions, we will take those.
Okay.
I'm going to move us along. I don't want to. I want you guys to be able to have time. All right, I'm going to get us started here. Welcome to this evening's plenary panel, Challenges in Geohazards Research in Alaska. I'm going to get off this stage because you've got a star-studded group up here. But before I do so, I want to introduce Brian Fisher. Off to my left here, your right. Brian directs the State Division of Homeland Security and Emergency Management for Alaska. He wears a lot of hats. He sits on the Alaska Seismic Hazard Safety Commission. He's on the board of directors of the National Emergency Management Association. But a little closer to home, he has played key, important roles. Hopefully you are aware, all of you, that the Anchorage area was rocked in November 2018 by a magnitude 7.1 intra-slab earthquake about essentially 50 kilometers directly beneath us. There was solid 50% G shaking across much of this region. That was a long period of going through a lot here. And during the response, the immediate response to that earthquake, Brian served in the role of incident commander, and then during the recovery period, much longer, he served as the state coordination officer. Those are deeply meaningful. So Brian, thank you for your service, and welcome to the SSA stage.
Thank you very much, Mike. I appreciate the introduction. I know you guys have been welcomed a couple of times already. You guys had some field trips on Monday, and you had some sessions yesterday. But on behalf of Governor Mike Dunleavy, the 12th governor of this great state of Alaska, I wanted to welcome you to Alaska, welcome you to Anchorage. Most of you probably haven't heard me say this before, but I say it all the time when we have visitors to our state. Please spend your money and pick up your trash, and we'll thank you for that. I just wanted to say, on behalf of the governor and my whole team at State Emergency Management, how happy we are to have the seismological community in the United States and our partners from countries around the world here in Alaska. It's particularly meaningful to us. I know you all know this, but it's the 60th anniversary of the 1964 Great Alaska Earthquake, largest earthquake in North American history and the second largest in history on the planet. So it's a meaningful year for us. The fatalities that occurred there, to the overwhelming destruction that happened in this area where you are right now, is something that many Alaskans don't and haven't forgotten about. It is extremely challenging to operate in this state. As an emergency manager, I'm a recipient and a beneficiary of all the great work that all of you do. We have just a myriad, a plethora, a veritable cornucopia of challenges in the state when it comes to mitigating the response to disasters, geohazards included. We have, a lack of robust data for this state. The data that we do have may not be the best quality. We have a lack of density of instrumentation on the seismic side. So we struggled just on the seismic side to deal with understanding at a practitioner level how to respond and save lives and protect property in this state. So the work you do is incredibly valuable to us. I think I'll keep it short there. Like Mike said, we have a panel of rock star Alaskans here that are going to talk to you more specifically about the challenges we have in research. But I did want to say thank you, again, on behalf of the governor and my whole team and all Alaskans for the work you do. It's very, very impactful. The way we respond to the challenges that we have with climate change and sea level rise and how that affects tsunami inundation, the more frequent and intense storms we have that cause significant challenges with landslides, the way we respond to that at the ground level in Alaska is, we're blessed and we're cursed. We're a big state. Time, space, distance, geography, weather, climate is all challenges. But there's only 730,000 residents in this state, and we have a few million visitors a year. So we all know each other. So the folks that you're going to hear from, I hope you've met them already. My team works with their centers and their offices on a constant basis. We know each other by first name. We've been throughout the state trying to help our folks prepare for the next earthquake, the next tsunami, the next landslide hazard. So with that being said, I'll just do a couple of quick introductions. I do appreciate the contribution of all of you in the scientific and the research community to helping, because what you do really saves Alaskan lives, so thank you for that. So I'll just do a quick introduction, and they can introduce themselves more as they come up to speak. I'll start to my immediate right, Elena Suleiman from the University of Alaska Fairbanks and the Alaska Earthquake Center is one of our tsunami numerical modelers. Who do we have next? Dennis Staley from the United States Geological Service, the Alaska Volcano Observatory. He's a research scientist for us. Jessica Larsen is a professor of volcanology at the University of Alaska Fairbanks, also with the Alaska Volcano Observatory. And then it's my great pleasure to introduce Rob Witter with the USGS Alaska Science Research Center. He's been a geologist up here in Alaska, I think, since about 2011. So certainly Alaskan. Rob, I'll let you take over. Thank you all very much for coming to our state and being here to work on this, these important topics for us. So thank you. Thanks, Rob.
Thank you, Brian. And thank you all for coming to our plenary on challenges in geohazards research in Alaska. So this is the roadmap of our discussion tonight. The four of us will summarize 3 key themes in 4 important topics in Alaskan geohazards. The 3 key themes are: how do we integrate social science into geohazards research in this great state? And how do we expose unrecognized geohazards? And then the pace of research in Alaska sometimes seems very slow in a changing society. So no doubt we live in a state with many, many earthquakes. And this is a map produced by the Alaska Earthquake Center that shows 45,000 earthquakes that occurred just last year in 2023. It also includes significant earthquakes in the past 5 years, including the 2018 Anchorage earthquake. The first theme I want to talk about is how do we integrate social science into geohazards research? And I want to focus on a paper by Adams and others titled "The Generational Gap: Children, Adults, and Protective Actions in Response to Earthquakes." This paper featured a video shown here of Anchorage School District students responding to the shaking in the 2018 earthquake by dropping, covering, and holding on. The perfect response. Adults didn't always do that. And what they found is that by recognizing how children and adults may react in an earthquake can improve drills and messaging, refine risk communication and strategies, and reduce injury and loss of life. But there's a big gap between social science and physical science in geohazards. And social science needs equal treatment. Get this fact: of the 10,000 USGS employees, only 8 are in social science, and there's only 1 that focuses on geohazards. And I consulted her in this talk. Thank you, Sarah McBride. In this state, there are many cultural and geographic barriers that make it difficult to communicate the information that we want to get out there about geohazards. But to reduce risk, geohazards need to be placed in social and cultural contexts. And to do that, it requires strong collaboration with social scientists. Okay, the next theme is unrecognized seismic hazards. And this is a change map. It shows the ratio between the 2023 Alaska National Seismic Hazard Model and the 2007 National Alaska Seismic Hazard Map. And it shows the ratio between the shaking hazard, and it shows a twofold increase in southern Alaska. These are challenges related to hidden and unidentified earthquake faults, geologic and geodetic data that just don't agree, uncertainties in ground motion models, and basin response to seismic shaking, which isn't accounted for in the new maps. But new work on the horizon, including proposed seismic imaging of the Alaska-Aleutian subduction zone and planned near-trench seafloor geodesy, has the potential to expose unrecognized seismic hazards in the future. Okay, so these are community internet intensity maps. They show felt reports or USGS did you feel it reports for two very different earthquakes. The one on the left is the 2021 Chignik, Alaska earthquake, a magnitude 8.2, and 268 respondents sent in felt reports for that earthquake. But the one on the right is from the recent 2024 New Jersey earthquake, which had over 180,000 responses. This is a new record for Did You Feel It? And it's obviously related to population density, but sometimes it feels like the pace of research in Alaska is like as slow as waiting for that next person to respond out in the eastern Aleutian Islands for a great magnitude 8.2. And similarly, earthquake early warning is a real challenge in Alaska. These systems require large and dense arrays of seismic instruments, and in Alaska currently we have 500 instruments across the state, so that's one for every 1,100 square miles, but this is very sparse compared to Japan and California, which are where early earthquake warning is implemented successfully, and they have much denser arrays. So challenges here include environmental ones, limited resources, the high costs of research, and almost insurmountable logistics, it seems. There's limited power and communications for the instrumentation that we need. And there are cultural, political, and societal pressures that often direct research outside. But something my close colleague Peter Heusler said really rings true. He said, if you want to know something about subduction zone earthquakes, you got to go to where you have subduction zone earthquakes. And he's right. There's so much we can learn about earthquake science in Alaska, and then we can take what we've learned and use it outside of Alaska, like in the Cascadia subduction zone, which is seismically quiet. So in summary, to reduce risk requires strong collaboration with social scientists. To expose unrecognized seismic hazards requires a lot of work and investment. And research in Alaska may creep along, but new discoveries about earthquake processes can increase societal resilience. Jessica.
I'm going to stand at the podium, actually. Okay. Okay, so next we're going to talk about the challenges that face volcano hazards research in Alaska. We have some of pretty similar challenges as with other geohazards research in Alaska. In particular, just some volcano facts for you. This map shows our most current elevated color code maps for our volcanoes in Alaska. So the green symbols are color code normal. Yellow is elevated unrest, and orange means we have an ongoing eruption at Great Sitkin volcano. So currently we seismically monitor 31 out of our 54 known historically active volcanoes. That number can change as we go to discover more and verify more recent eruptive activity from some of our unrecognized volcano hazards. Ash clouds and ashfall are our main hazards, and they have significant impacts downwind on populations on commercial jets, traveling the North Pacific routes, typically from North America to Asia, but also polar routes. And we have about 70,000 people per day on average on those flight routes. So that's a large transient population of sort of temporary Alaskans in these jets. We also have downwind hazards from our volcanoes that impact remote villages, as well as our main population center of the state, which is the Anchorage-Matsu area, where 400+ thousand people live. So we have a big job. Some of our challenges, particular to volcano hazards, are forecasting versus detection. To truly forecast an eruption, you need a really good, robust seismic network infrastructure because seismic monitoring is still our main way that we monitor these volcanoes. And that's a big job, and a lot of our volcanoes, as you can see from the 31 out of 54, are not seismically monitored at all currently, and others we have challenges with weather and winter and remoteness and all of those things that can cause network stations to go in and out. We can detect eruptions. We're really good at detecting eruptions quickly. However, we have some challenges there too. There's a time lag for satellite data. We only have certain passes at certain times of the day. Sometimes we have to wait for that data. And another tool we've been using recently is infrasound explosion detections. Those have a travel time lag. So some of those challenges are even there for rapid detection of our eruptions. Again, we also have the remote volcano problem, as a lot of our fieldwork has in the state. Logistics is challenging. We're resource limited. Takes a lot of effort and financial resources to monitor our volcanoes. And then weather is always an issue. And then we also face changing numbers of air traffic, increasing air traffic over the years. So for integrating social sciences, like with earthquake hazards, we also have very few dedicated social science and education and outreach professionals that we can tap. And limited personnel time is a big challenge for us. We also face similar cultural and geographic barriers and challenges. That's something that we're really working on a lot with the Alaska Volcano Observatory, as well as NSF project I'm involved with called Pre-Events. Our standard hazard assessment products were typically a map and booklet that explain the hazards from volcanoes that we have studied well. But the USGS is implementing some new ways of doing hazard publications. So the next-gen hazard assessments, I'm involved in one of these projects at Makushan Volcano, which is close to Dutch Harbor. It's a very high-threat volcano in our state based on the NUV's ranking. So we're moving beyond the paper hazard map and booklet there. We're co-developing some digital projects with locally relevant information with some of the community members and stakeholders in that area. I have an example up here. This is a Mount Rainier interpretive sign that is produced by the USGS Cascades Volcano Observatory. So we're going to be working on one of those products also in the Alaska Dutch Harbor area as an example of how we're trying to move beyond into sort of a next generation hazard assessment. Another example I'll mention really quickly is the Pre-Events NSF project that has been led by Taryn Lopez at the University of Alaska Fairbanks. Volcano outreach and education materials in this project are now in a phase where we are co-producing educational resources with community members. So these are Alaska Native elders and culture bearers and educators in those communities. So a lot of the lesson plans and educational materials are going to embed local knowledge. And it's a collaborative effort between the volcanologists and the community members to develop products that are really relevant for their communities and are driven by community needs. So unrecognized volcano hazards. This is a big challenge for us. We have greater than 90 Holocene volcanoes, which means volcanoes that have erupted within the past 10,000 to 12,000 years. Those volcanoes are geologically considered dormant, and they have the potential to reawaken. And a lot of them are largely unknown. So geologists haven't been able to do work on these given our challenges of remote work environment, weather, and summer season work only. The high cost of Alaska fieldwork also can be a barrier for out-of-state researchers to come up here to do big field campaigns. So personnel is really limited. So even if there is an known unrest, we cannot always just immediately travel out to our volcanoes, particularly those out in the Western Aleutians, for example, or in the winter. It's really challenging for us to do that. I have two examples up here. One is a deformation map on the top from Grapentine et al. 2022. Mount Edgecombe in the southeast Alaska area went through a period of unrest that is continuing off and on. First produced a seismic swarm. The residents in Sitka noticed the seismic activity. And so the geophysicists were working on some geodetic modeling with INSAR data. So this is a satellite radar, synthetic aperture radar method to look for volcano deformation. And sure enough, found that Mount Edgecumbe was deforming significantly. So Mount Edgecumbe is actually now on our map of monitored volcanoes. So we were able to install a good enough seismic network around Edgecumbe. The bottom picture is one I like to show. This is Four Peaked Volcano in 2006. I will never forget a quote Judy Fierstein, an eminent USGS geologist, told us when this Four Peaked steam explosions, which is the photo I'm showing on the bottom image, she said, "Wow, we just thought that was an old dead volcano." And it produced, 15,000 foot plus steam explosions that were visible from Homer. So that really got our attention. That was a truly unrecognized volcano hazard. The pace of volcano hazards research also is a challenge, and we face, the same pace of research issues with the remote work environment, the difficulties of working in Alaska. However, it's also uneven. So geophysics and gas monitoring can be relatively quick and often is in real time. But eruption histories that are done by geologists, these are things like tephrochronology, geologic hazard mapping, full geologic mapping to fully understand the hazards that a volcano can produce and its eruption frequencies. These are critical for forecasting tools and hazard assessment, but they just take time. It's really rare to have a one field season complete hazard assessment and eruption history for one of our volcanoes. I don't think that's ever happened. So it just takes time. So that is a big challenge for us. So I just wanted to touch on some of these examples just to highlight some of the challenges that we face for volcano hazards research in Alaska, similar to earthquake hazards research. And hopefully this seeds some ideas for questions that you might have for the remainder of the plenary.
Hey, thank you so much. It's a real honor to be up here tonight to speak with you. I'm going to be shifting over to landslide hazards. And the quote at the bottom of your screen there is related to mountains, but I think John Muir probably meant that both literally and metaphorically. And I think metaphorically it can also be applied to landslides, that Alaska is full of grand and glorious mountains, many of them in the clouds, but not all hidden. And so that brings us to our first theme, which is that of unrecognized landslide hazards. Many of you were probably out on the boat on Monday. You had a beautiful day, it sounds like, and saw the Barry Arm landslide, maybe for the first time. That's a perfect example of an unrecognized hazard in a vast landscape. Here we have a landslide, slowly moving landslide that's 2.5 kilometers wide by 1,000 meters high that nobody even knew about until 2019, when a group of citizen scientists and academics put together an open letter that attracted a lot of media attention and attention in Congress. And all of a sudden, a lot of eyes were trained on landslide hazards in Alaska because of the important work that this group did initially. And so now we're looking all over for where we may see potentially other unrecognized landslide hazards. My colleague Lauren Schaefer recently applied a persistent scatterer INSAR method to the region around Prince William Sound to look for other slow-moving landslides that we didn't know existed before just a few months ago. And her work, along with that of her colleagues at Southern Methodist University, discovered 43 new slow-moving landslides across the Prince William Sound region, 11 of which, that are in blue, have the potential to have some material plausibly end up in the water. Now, a great deal is not known about these landslides yet. We don't necessarily know the volume. We don't know much about the runout potential of these landslides, but we now have 43 new landslides on our list that we need to think more carefully about and do more analysis to better prioritize how we approach those moving forward. We also have shallow landslides in Southeast Alaska. We know Southeast Alaska is steep, we know it's tectonically active, and we know it gets a lot of rainfall. Those are the key ingredients for the initiation of shallow landslides. But oftentimes, these will initiate during rainfall that's not particularly remarkable, or in places that aren't uniquely different from any other place in Southeast Alaska. And so it's up to us as landslide scientists to better understand why these are being triggered in those locations and at that time and in those conditions. So we have lots of tools we can apply to it. We have satellite remote sensing. We have on-the-ground monitoring. We can monitor what's happening above the surface, the rainfall coming down, what's happening in the subsurface. We can do the things that Mike West talked about in his presentation earlier today, looking at seismic and other non-seismic data sources that will all help us better untangle why these landslides are where they are, why they move when they move, and why they fail when they do. Now, I will admit, I am a geoscientist and not a social scientist. So my main lesson that I've learned is to listen to the social scientists and let them help us inform our messaging to the public, to these communities that we go out to. We're very good at applying modeling techniques and assessing in the graph on the left, the time of a wave arrival and the potential height of that wave in Whittier. We can then compare that to pedestrian travel time maps. We're very good at doing those things, but we could definitely use work as geoscientists and how we message that, how we go into communities, understand their culture, understand their risk perceptions, understand their risk tolerances, and tailor our products and our communications to them. And so my challenge to all of you is when we're out in the field talking to boat operators or when we're talking to the military as they plan out their tabletop exercises, to really listen to what their needs are and take that back and reflect on that when you're preparing your research plans. The pace of research, I'm so glad I'm the first person to make a glacial joke. So you could say research moves at a glacial pace, but I think that's a little bit unfair in Alaska because we have a lot of glaciers that move really fast. So we had the terminus of the glacier by the island there in 2006, and then it's kind of been hanging out in that location since 2017 out in Barry Arm. So about 3.25 kilometers in 11 years or so. So the landslide work in Barry Arm started 3 years ago, so I guess we still have 8 before you can really fairly compare us to a glacier. But we've talked about the weather, we've talked about the conditions. Those are obviously a challenge. Just getting out to Barry Arm can be an adventure in and of itself. You have lots of snow, you've got clouds, you've got wind. Your sensors can be damaged by incredibly strong winds or buried under feet of snow, making telemetry very difficult. We also have a really complicated landslide out there. So it moves in different pieces at different times. It's got a very complicated failure surface geometry. So many of the tools that we're used to applying to more simple landslides just aren't necessarily applicable directly to the Barry Arm landslide. So you combine those factors with the factors of how we all know how difficult it is to produce relevant and fundamentally sound science and how long that takes. It just geometrically increases the amount of time it takes to produce that quality research. And that's not to forget about safety either. So we work in Barry Arm at a big, deep-seated, slow-moving landslide with the potential to fail catastrophically into the water and generate a wave. And we need to remember that when we're considering the safety of our field crews. So this is an image from our radar. We've got a ground-based radar in the fjord trained at the landslide. We like to see shades of green. That means the landslide is either not moving or moving away from you, which really isn't physically plausible. But when we log in and we see these reds and purples, that means the landslide is starting to move towards us at a rate of somewhere between 50 to 150 millimeters per day. So that affects all of our operations. We travel 50 kilometers by boat oftentimes to get there. We hike up to 200 meters to our radar site. We can't do those things when the landslide is moving because of the risk that our field crews take. So that also slows down the pace of our research and our operations because we've seen over the past 3 years this landslide slowly move several times throughout a period of months in the late summer and fall. So that pretty much quickly summarizes the challenges of landslide hazard research in Alaska. I'll turn it over now to Elena. Thank you.
60 years ago, during the first 12 hours after the main shock of the Great Alaska earthquake, 10 waves inundated Kodiak Naval Station. Rob and I are standing right there next to the high water mark of the 1964 tsunami. Thanks to the personnel of the Kodiak Naval Station, we have a precise record of those waves, to the minute, both the arrival times and the amplitude. 60 years ago, the word tsunami was not in the American dictionary. They were called seismic sea waves. And what's so special about tsunamis in Alaska? They are near-field hazard, which means that the coastal residents have minutes, not hours, for evacuation. So the near-field hazard in Alaska, near-field tsunami hazard, is defined by two factors: the active plate boundary and the glacial fjords. Because of that, the majority of people who died in 1964 died from local landslide tsunamis. Alaska also holds several records for the highest waves observed. And as you just learned, the Barry Arm slide is not alone there. There are at least 43 more sitting around Barry Arm slide, and this is where we live. The little tiny red dots there are coastal communities, and you can see how close they are to the rupture of the major tsunami-genic earthquakes in the past, and some of them are actually even within the rupture zone. This is what we call near-field tsunami hazard. On the first theme of integrating social science, going to coastal communities in Alaska over the past 20 years, unfortunately, I've realized that the 1964 tsunami have been forgotten in terms of the young generation doesn't even know about that. In coastal communities where elders come to me and tell me heartbreaking stories about what they remember about 64 tsunami, students in high school had no idea what happened in their communities in 1964, and this is actually heartbreaking. So this is the only memorial that I am aware of in Kodiak. That stone is located somewhere between the McDonald's and the fire station, and it says the high water mark of the 1964 tsunami was there. However, in Japan, in just 13 years, they built multiple museums and multiple memorials that save the past and contribute to future life-saving. The biggest challenge working in coastal communities in Alaska is that extreme tribal and cultural diversity. There are so many tribes and communities with different cultural and religious backgrounds. And for example, at the top is the cemetery in the village Uzinkie in Kodiak that was totally destroyed by the 1964 tsunami. Many people died there. And that community is extremely proactive in tsunami preparedness. They built a new tsunami shelter just recently. They applied for funds to build a vertical evacuation structure, believe it or not. And at the bottom, there is a tribe called Haida in Heidelberg, Southeast Alaska. They never experienced a tsunami, but in their culture, there is a god called Volcanic Lady. And the mayor here on that photo is building a totem pole with the Volcanic Lady face on it. And he says the Volcanic Lady, when she gets mad, and she was mad in the past, she sends some ash and a huge wave. So this is the oral history that gets kind of transferred from generation to generation. And you need to know those histories in order to apply the proper message and to convince them that, yes, you need to think about tsunamis, you need to talk about tsunamis. So we know that the most costly unrecognized hazard has been tsunami in this century. In the Indian Ocean tsunami case, yes, it was unrecognized hazard. If the hazard had been known, the tsunami science was advanced enough to create tsunami maps for the entire Indian Ocean coastline back then. But the 2011 Tohoku tsunami, it was a different story. The hazard was realized, but it was greatly underestimated. And even 60 years after the 1964 tsunami, we just discovered a missing tsunami in Upper Cook Inlet, and that story will be tomorrow in our poster session. Please stop by and I will tell you the story. So the big question is, of course, where is that unrecognized tsunami hazard sitting right now in the Alaska Aleutian subduction zone? So we've been working for the past 25 years to create tsunami hazard maps for coastal Alaska. Last year, we published the tsunami map for Anchorage, and we are here in that building. So we are pretty safe today. The challenges are the following. The biggest challenge, of course, is the near-field tsunami hazard, which means that the sensitivity of the local tsunami wave field is, to the slip distribution is enormous. For example, this is the animation of the 1964 tsunami coming from the Kodiak Asperity to the island of Kodiak. And you can see how dramatically different the arrival times can be depending on the slip distribution. So the red color represents uplift and the blue color is subsidence. And you can see that the tsunami wave field is far from being intuitive. You cannot describe where the waves are going to travel because the bathymetry is so complicated. So that sensitivity creates a special challenge, especially in advancing into probabilistic tsunami hazard assessment. We have uncertainty in geometry of the previous tsunamigenic ruptures of all the earthquakes along the Alaska-Aleutian subduction zone. We don't know the slip distribution for the 65, 57, 38, 46 earthquakes, but it would be nice to know the slip distribution, of course. We have relatively short paleoseismic and paleotsunami records in the state, and of course limited modern data and topography gaps and bathymetry gaps. So these are my questions for you. What would be our plan for the next 60 years, given that we even have 60 years? I leave it here, and I'm looking forward to your ideas. Thank you.
Thank you, Elena. Thanks, Dennis. Thanks, Jessica. I'm really proud to be sitting up here with you guys. We have a lot of challenges in Alaska and geohazards, and we're open to questions from the audience. Did I hear Sarah McBride in the audience? Is Sarah here? I talked to Sarah to prepare for the talk, and one of the ideas she gave me immediately was, you should invite a social scientist to your plenary. And she's right. I wish she was up here today, because there really is a gap between the social and physical sciences and the applied aspects of what we do to save lives, to reduce risk, really requires that tight collaboration. Are there any, what can you guys, can you add to that?
Let's just listen to the audience.
We're doing a Q&A now. Should I come
Yep.
to the...
Oh, wait, somebody's at the mic.
It's okay, you can go first.
Oh,
Sorry, you
go ahead, Hig.
All right. Hi, thank you. It's Mark Quigley from the University of Melbourne. I think we'd probably agree that the best science in the world, geoscience in the world, isn't going to save us if it doesn't engage meaningfully with engineering and with land use planning, and of course some of the social science aspects that you mentioned. Now, I've come from the other side of the world, but I had a lot of experience in Christchurch in the post-disaster context there. And two observations that I and many of my colleagues made when we were here, and then I hope that stimulates a response. The first was on the field trip, we drove by a building, I think it's called the Inlet Building or something, with these big pictures of it after the 1964 earthquake with these big X-shaped cracks all through it. It's still there, and the comment was made that it was sort of patched over. And I wonder whether this is the sort of low-hanging fruit that we would recognize it as a real risk of a collapse or major damage in future earthquakes, and what sort of advocacy is being done there. And I don't know, it's just an observation. The second one is for those of us who've done the coastal trail, walked or run along there. It's very obvious that a whole bunch of new properties, beautiful homes, have been built right on top of translational landslides, sometimes right across the headscarps and all that sort of stuff. Now, we know that if you allow people to build, they will build. Doesn't matter. Again, that seems like fairly obvious low-hanging fruit because we know that those things were landslides, but there's obviously a policy that allows for development there. So how much more science do we need versus, I guess, can you comment on any of those kind of aspects that are quite obvious to geoscientists, but maybe not to others?
Well, I'll respond to the building question. Anchorage has modern building codes and follows them. And I think the 2018 earthquake is a good example of how stable and stout our building stock and infrastructure is, and we do very well. I'm not an engineer and I'm not a planner, but that building appears to have some superficial damage to it that was patched over, and it seemed to hold up in the 2018 earthquake. It is an important issue, but I think Anchorage stands out as a city that successfully can stand up to earthquake hazards like we experienced in 2018.
This isn't earthquake related, but for volcanoes in the state of Alaska, most of our hazards are from volcanic ash, so ashfall and ash clouds downwind. However, there was an infrastructure challenge with the Drift River Oil Terminal, which is downstream of Redoubt Volcano, which, when it erupts, the lava dome and pyroclastic flows melt the summit glacier and create really, truly colossal lahars. I think the stream flow rate is similar to the Yukon for some of these lahars. They're massive. So the Drift River Oil Terminal downstream, they had a lahar safe house. They built levees around their storage tanks. So this was a sort of an intermediate oil transport and storage facility, and from Drift River it was offloaded onto tankers. And the reason it was there is because the bathymetry was really good for a tanker to come in, to pull in and get oil loaded. So that was a real challenge during the 2009 eruption of Redoubt. There was a lot of challenges associated with keeping the workers safe out there from the lahars, and there were lahars during that eruption. There pretty much always are. That facility has since been decommissioned. So that's pretty much the only infrastructure-related challenge I can think of in the state of Alaska for volcanoes with on-the-ground hazards like that. There is a real tension around the world, though. Another example I can think of is in the Democratic Republic of Congo in the city of Goma. Nyiragongo volcano erupts really low viscosity types of lava, and when fissures open up right outside of town, those lava flows can be deadly. And if you look at imagery from satellite, people have rebuilt there in the same regions that were inundated by lava in the last eruption. So I just wanted to point that out, is there's always a tension between the economic driving forces of development and the geohazards. And I just feel like around the world, we just haven't caught up with how to really address that problem. It's a real challenge.
I wanted to kind of riff off of Elena's planning question here, and I'm kind of wondering. I think the question I have is sort of how do we plan? Like, if we are trying to picture 60 years or even 15, maybe something like this, it's a little bit beyond our usual like budgets and grants and stuff. And I mean, in my little intersection with these topics, I've been like, part of my mind is like, I need to build one of those things with the pictures and the yarn stretched between it to try to figure out what's going on. But I've also had conversations with Murkowski's office about developing policy paper that would help guide future funding processes. I've had conversations with people who think in terms of business plans, and like there are all these different structures for how do we take what for me often feels like so many things that I'm grasping at, and I can't keep track of them, put them into some form that will allow us to communicate and coordinate and move towards some of the goals that maybe we haven't even fully articulated out there. So anyway, I'd love to hear anyone's comment on that.
That's a really challenging question, but I'll give it a shot from the landslide side. So you think of the long-term plan for landslide hazards and landslide hazard research in Alaska, and I want to look back first. So thinking 5 years ago where we were at, USGS didn't really have much of a presence doing landslide work in Alaska yet. We didn't know, thanks to your work and your colleagues Hig and your sister, we now know about the Barrier Arm landslide. So how far we've come just in the 5 years since the recognition of the Barrier Arm landslide hazard has been really, truly remarkable. I think we have made some missteps along the way. I think we have learned a lot of valuable lessons along the way. And, you know, thinking about the long-term plan and changes in the support of science through the National Science Foundation or through the federal government, it's important for all of us that are involved on the governmental level, at the state, at the federal level, while we work very well together, is to, I would challenge us to do a better job of engaging with the academic groups so that we can have a longer-term, sustainable approach to landslide science in Alaska, so that when we trip up over ourselves and fall and have to pick ourselves up and dust us off, the academics are there to help prop us up, to get us through those lean times of budgets. So I would encourage all of us to work a little bit better, myself included, to reach out to these academic groups, these nonprofits, to set ourselves up for continued success with always that constant uncertainty on budgets and scientific support.
My greatest concern is how industries in Alaska build in the tsunami hazard zone and keep building. And I just don't know how to deal with that. It's so heartbreaking, like what they're doing now in Witter at the waterfront, at the head of the delta where it collapsed in 1964, and it will collapse again, like in Seward and Valdez, similarly. So the question is, like, what do we do? What is that agency? What is that kind of entity that can prevent building in the tsunami hazard zone?
I don't have much experience in that area, but it seems to me that passing the word to them, I mean, I hate to put it in base levels, but how their loss is going, explain to them how it's going to be a larger loss for them if they aren't thinking in certain terms. I mean, it might be a matter of time frame. They might be thinking about short-term loss, and they're going to, you know, I mean, look at the oil, you know, the oil disaster. They suffered quite a bit. If some of these industries, before they build some of these things, could be given a little periscope into the future of how much it's going to cost their bottom line. I mean, you know, and to whatever channel you need to go through to make that point, just to, you know,
Yeah.
I don't know.
The hardest thing ever. Mm-hmm.
So I have a question about tourist season. And so there's probably a huge influx of people to places like Kodiak in the months of July and August. How do you deal with communicating hazards to people who show up to fish salmon and look at bears?
So recently we started making tsunami brochures for coastal communities in Alaska, and they are very community specific. So we have that glossy, shiny brochure with the tsunami hazard map inside, with all the important locations on that map, including the tsunami shelters, schools, hospitals, and so on. But it's up to the community to distribute those brochures to the tourists and to the businesses. And not all of them are actually welcome those brochures. Not all of them want to show them to the tourists because they don't want to lose that money flow into the state. But some communities, like, for example, Skagway, they do recognize that extreme hazard, because when they have 5,000 to 10,000 people walking through the town, and they know that tsunami can happen there because it already happened there before, they're thinking how they're going to evacuate those tourists, because the cruise ships will leave immediately when the tsunami comes and when the tsunami warning is issued. And those 10,000 people are in Skagway, cannot go anywhere because there are no roads anywhere. So the fire chief in Skagway thinking about bringing buses from Canada and driving them to Canada, to the nearest airport. Yes, so basically it's up to the community to decide what they want to do with that. But I can tell you how resistant some of the communities are in terms of educating tourists about tsunami hazard. It's a big issue.
At high latitudes, the climate is changing faster than other places on the globe. And so what kinds of impacts are you seeing or expecting to see on the hazards that you study? And what do you need from this community to prepare for hazards that are potentially impacted by climate change?
Thanks. I guess I'll take this one to start. Landslides obviously are affected by the processes. Maybe I won't start. But landslides are obviously affected by climate change. We look for the recession in advance of glaciers and the effects that has on landscapes or exposure of new slopes that may potentially fail into the water, changes in the duration, amounts, and intensities of precipitation that may trigger shallow landslides. And climate change certainly has an impact on those. And so what we can do is try to better understand what those shifting patterns are and predict and forecast what might happen in the future as we apply the different climate models and downscale them to an appropriate scale for the processes that trigger landslides, which is a really difficult thing to do. But to also look for places that may be vulnerable in the coming years, from glacial recession, and to forecast where those areas might be. So just grasping the problem under a range of different scenarios is probably, in my opinion, one of the easiest approaches that we can do at this time as we learn more and more and are better able to forecast what those effects of climate change might be.
I think from the volcano side, we have a lot of ice and snow-covered volcanoes in Alaska, and I'm just going to say that I'm not sure we know what the impacts are going to be when a lot of that ice mass is lost. There's some indication, I'm not an expert in this particular field of volcanology, but there is some indication that when the big ice sheets started retreating and we had kind of the end of the last glacial maximum, we had some pretty large eruptions out along the Aleutians. And it's just kind of a curious question. I'm not going to speculate on what the linkage there might or might not be. But I do know, just from my own experience out in the field, for example, the Summit Glacier at Makushin Volcano, I noted last summer, it just looked like the ice volume had deflated relative to when I first started working out there some, 12 or 13 years earlier. And so I think one of the things I would really love to see is more work just mapping the ice mass loss from some of our volcanoes. I know there are a lot of really talented glaciologists out there, especially in the state, but also around the world. And I'd really like to better understand what we might be facing in the future, if the volumes are even big enough to make any sort of stress difference inside the magma reservoir that might trigger eruptions or not, or what are some other things, some other unrecognized hazards we might be facing as some of these snow and ice fields and glaciers are basically dwindling away.
Yeah, I have a comment about earthquakes in response to climate change. Interestingly, the ripple effect of sea level rise can raise the amplitude and sea level heights of tsunamis. So tsunami waves generated by earthquakes along Alaska's subduction zone will be more damaging if a projected sea level rise over the next 100 years occurs. The tsunamis will ride on that higher sea level, and if ports and harbors, say in Southern California, which are in line for a big earthquake in the western Kodiak region, for example, a big earthquake in the western Kodiak region would project a tsunami straight down to Southern California. And today it would take something like a magnitude 9.1 based on a safer scenario, which was a USGS tsunami study. And it would produce currents, damaging currents, and wave heights that would damage those port facilities and probably great hardship on transportation in the western U.S. If sea level rise continues, those risks would be exacerbated.
Hi, I just had a comment about the pace of discovery and the pace of research, and you know, I know despite the challenges here that were so eloquently outlined by all of you all, I just wanted to point out that it seems like the pace of the discovery is pretty rapid, actually, and you and your respective groups and colleagues, it seems like, you know, you have the pedal on the metal as far as the resources that you have and the work that you do. And now, I used to live in Alaska, but now I don't, and I sort of am observing from the outside what's going on here, you know, and it seems like a lot's going on. The pace of research is actually pretty rapid given what you have and the challenges. And so I just wanted to say, I wonder if you have any, not just you guys in the panel, but a lot of other people in the room here doing a lot of work. But do you have anything to say about how you can encourage more people to do work in Alaska in these respective fields, including maybe some graduate students that might be in the room and things like that? Like, how do you encourage people from the outside to come here? Because it's a really big place and you can't do it all yourself. That's it.
Yeah, Rich, thank you for that comment. It is a really big place, and the work that the USGS in my office gets done on earthquake hazards is a team effort. We involve both academic and other USGS colleagues in all of our research, and we also have worked with students from our academic colleagues, and several of those students are in this meeting right now. So that's a really good point, and if you're interested in working in any variety of geohazards research, please come up and approach us. That would be great.
Yes, we are looking for tsunami scientists to come to Alaska. Please consider.
I'm just going to say, don't be afraid of a little rain and fog and wind. I've worked in the Aleutians for a long time, and I think that there's a mystique about working out there, and I've really enjoyed it, actually. I think that, you know, the Volcano Observatory really welcomes collaborations, and there have been a number of successful cost-sharing efforts with big NSF programs, smaller NSF programs, and I think it works really well. So there's really been a real desire and drive and push to work with scientists from outside of Alaska and even non-observatory scientists within Alaska to try to get people out into the field and to help support broader research. And students, we really like to also get students in the field. And you know, the Alaska mystique, really, when you get here and you start working, it's not so bad. It can be pretty fun. It's challenging, but you know, we get the work done, and it's not quite as bad as people might think.
It's nice to hear that we're viewed as making progress too, because I think, you know, landslide years are like dog years in many ways. They age you, and it's hard to see the progress when you're kind of in the trenches trying to make progress. So that's really kind of you to say, and very appreciated, I think, probably by all of us. In terms of attracting people up here, yeah, the boat ride probably did a nice job of attracting people to live in Alaska. But it's not normally like that. It is a little bit more challenging. But the publications that people do where you're using remote sensing or analysis of seismic data, where you don't have to be located in Alaska to do that work, you know, those are the kind of things that can attract attention to the problems that we face here. So encourage everybody to continue doing that excellent work that you're doing back in your respective homes. I would want to push on a little bit, though, that I think we can do a better job of engaging people in Alaska, too, especially in the Native communities. So at the USGS, I think one of our initiatives is to better engage with Alaska Native Science and Education Program. And there's opportunities there for Alaska Natives or people that are attending Native supporting institutions to have internships with government agencies and the USGS in particular. So encourage people that you know or your colleagues in academia to explore those websites and to get those underserved communities better represented within geosciences. Thanks.
Thanks, everyone. I'm just thinking about cascading hazards. So, you know, an earthquake triggers a volcanic eruption. I know that's controversial. But then the volcano has a slope collapse that then triggers a tsunami. So not necessarily an unrealistic scenario to kind of have all of these at play here in Alaska, or 2 or 3 together. So I was just wondering your comments about that, about communication between these different disciplines. What are some of the wins, or what are some of the challenges, and how we can work better together moving forward?
There was a eruption of the St. Augustine volcano in 1883 that resulted in the collapse of the part of the volcano and in the tsunami that was recorded across the bay in the little village by Alaska Commercial Company Trading Post. And yes, that volcano is active, and we mapped that hazard in the tsunami inundation mapping report. Together with the tectonic tsunami scenarios, we consider a potential collapse of the volcanic flank in case of an eruption. So we do include volcanic tsunami sources as well as landslide tsunami sources in our tsunami studies. So this is, how much we can contribute to that.
That's a crazy dream that you just put in my head, because something like that could happen. And I think we need to work harder at communicating between interagencies and setting up a plan beforehand on how to respond to an after-event sort of thing, but also be sensitive to the communities that are going to be hit hardest. I think it's very important to make sure that we're most sensitive to safety and saving lives before we go in there and study things. But yes, strengthening our communication and our networks, I think, is really important for the next big one.
I think that you just made a really good point, because last summer when we were out doing volcano fieldwork in Makushin Volcano out in Dutch Harbor in Alaska, we were asked about tsunami hazards, and it just triggered in me that given the remoteness of our communities and the logistics and traveling out there, I think you make a really good point that even if we're not dealing with a cascading hazard per se, it would be really good. I plan to bring some tsunami materials out with me this summer to Dutch Harbor, because I have Elena's beautiful brochure now. So I'm going to be much better prepared to talk about multi-hazards when I'm out in these communities from now on.
Yeah, I agree that everything pretty much boils down to educating people in those communities. Lori Denger just recently said that the success of any warning system actually depends. Actually, the success means that we can get people out of the way before the water comes. And that's it. So it means that if people in Homer know that when St. Augustine starts erupting, the wave can come after that. It's not just the ash. There are multiple hazards. And until we know that people in Homer are aware of that, and especially the tourists who come to Homer Spit during summer months, this is the most important thing, pretty much, educating the people so they know exactly what to do. Sometimes they don't have much time to evacuate. They don't have much time for advanced warning. And that work, it just needs to continue, because we don't know when the next one will happen. It can be 100 years from now. So that's why we just need to keep talking about those hazards.
I was thinking about the great comments on the need for social sciences in this and communication, which aren't necessarily exactly the same thing, but closely linked in the comments about people building their house on a headscarp. Actually, I'm working with a couple that live in a house that is moving and rotating on a landslide, and they've had to jack up their house. And we've got an instrument. I don't know if that helps them at all, though. And so I understand that part of it, but I'm imagining if some of the people I've worked with were here in the room, some of the community members, and especially some of the people I've heard express frustrations, that some of them would be saying, well, wait a second, I'm on top of this, but when I reach out for help and such, then I can't find that, or I, talk to people at one level in an organization and they understand the place where they are and they're worried, but then when they look further up in their organization, then they don't get that support there. And I think that there are things to be learned for all of us as a community about how to put ourselves more on the same level as the people that we're interacting with. Just to pick one example, then I'll stop rambling, but probabilities. Like, I think you'll often hear scientists be like, well, yeah, I was working on the probabilities of these things, but nobody listens, nobody understands, it's worthless. Like, I can't even talk about this when I'm talking to the public. And it is really challenging, but I don't think we should give up. I think fundamentally some of these questions we have are probabilistic, and I actually do think, humans in general are capable of understanding that at a useful level, but we aren't doing a good job of engaging as our part of those conversations. So anyway, that's my comment, invitation.
Thank you. I agree it's the hardest thing ever to talk to public about probabilities, because I just don't have the vocabulary for that. It's the hardest thing. So we need to develop that vocabulary, right? And that's why we need social scientists, I guess.
Yeah, I'll agree that talking about probability is very difficult, as is talking about uncertainty in the estimates that we are able to provide. We can certainly do a better job in describing those in a way that's meaningful and impactful to those that are in the audience. And I guess we're all in that boat where we all can try to figure out better ways of doing that. And the fact that we're even talking about it is a great start. In terms of addressing the needs of all of these communities that are at risk for some type of geohazard in Alaska and beyond, that's really difficult for all of those reasons we talked about before that are related to the pace of research. And in the places that we're currently working, we want to answer the questions that we set out to do in those locations too, and that all takes time and people and resources. So there's not a great answer to that, but it's just the communities continually piping up and saying things and talking to their representatives so that the National Science Foundation can get better support, so that the scientific agencies can get better support. That's the beauty of our system, is that people do have a voice. And I hope that people will take advantage of that opportunity in these affected communities. And we also have to go into those communities recognizing that each one has a different acceptance and tolerance of risk and what they want to incorporate into their planning and their emergency management and those types of activities that are really largely up to the individual community.
So the question of uncertainty and probabilities also can be challenging for us scientists as well when we develop volcano forecasting tools. So these are often probabilistic models that take into account a lot of different things, and they're time resolved, starting from unrest and then moving in a progression through an eruption scenario. And we need to, the times I've participated in these, they're called expert elicitations, to build like some sort of event tree. We call them event trees for volcanoes, where you progress through a series of most probable events to try to forecast what might happen. The question of uncertainties is challenging for us as well, because we don't always know the magnitude of the uncertainties on any sort of observation or threshold that we want to put into these forecasting tools. So we struggle with that too sometimes, and as we go through time, I think we're getting better at it for these products. In terms of when we talk about sort of outcomes with the public, with the Volcano Observatory, we most often cast it in terms of scenarios. So a most likely scenario for this eruption is X, based upon what we see now with the monitoring data or what we know about the past from the volcano. So we don't typically put like probability numbers in there, but we try to talk about it in terms of scenarios. And I honestly don't know. I mean, I'm so embedded in the science, I don't know how a person in the community views those things. So it's a really good question.
All right, I'm gonna close us up here. Thank you for being here. 4 hazards, 4 specialists. You know what they look like now. I encourage you, find them in the hallways, stop them on the escalator. It is clear they have lots to share, and I encourage you to use them as resources. Thanks again, and how about a round of applause for our speakers.